Alright, so we're in section 2.3, part 1. Alright, so the first thing we want to do is we want to remember how to divide polynomials. We're going to do an example of dividing a polynomial, one polynomial by another. So I want to divide 2x to the third minus 5x squared plus x minus 8 by x minus 3. So we're going to write our division. We're going to do long division first, and then we'll talk about a shortcut, because the shortcut doesn't always work. So just like if we were dividing numbers, I'm going to write it like so, x minus 3. And then what I ask myself as I'm doing this problem is I look at this first term, and I say, what do I have to multiply x by to get 2x to the third? 2x squared, and I write that up here. So I write the 2x squared up there, and now I'm going to multiply 2x squared by both of these. So 2x squared times x is 2x to the third. Multiply here, and I get minus 6x squared. Yes?
I'm confused when you got 2x squared.
What's that?
I'm confused when you got 2x squared.
I said, what do I need to multiply x by to get 2x to the third? So I know 2x.
How come you don't do anything with it?
So all we're worried about is that we just have to worry about that first number. So it's like when we divide, if we were doing like 62, 61 into 7213, for example. I say, how many times does 60 go into 213? Rather than, I don't worry about the 61, I say how many times does 60 go? Same kind of idea.
Right, 0. Okay.
All right, and then here's where students usually get tripped up on long division. We subtract. So I put parentheses around everything, and I'm subtracting. 2x to the third minus 2x to the third is 0. That's why we did that, because that goes away. 5x squared minus negative 6x squared. 5x squared plus 6x squared, I get an x squared. And then I bring down that x. And now I say, what do I have to multiply x by to get x squared? X. And I write that up here. And then I multiply this by both of those. So I get an x squared minus 3x. And put parentheses, and I'm subtracting. X squared minus x squared, that goes away. That's why we do this. X minus negative 3x is 4x. And I bring the 8 down, the negative 8. And I say, what do I have to multiply x by to get 4x? Plus 4. Multiply, and I get 4x minus 12. Subtract, those go away. And negative 8 plus 12 is 4. So what this tells me is that 2x to the third minus 5x squared plus x minus 8 divided by x minus 3 equals this part, 2x squared plus x plus 4 plus the remainder. This is my remainder. 4 over whatever I divide it by. We'll call this the remainder. Yes?
Why did you do this 6x squared after the second step of the division?
I multiply this by both of these. So 2x squared times x is 2x to the third, and 2x squared times negative 3 is negative 6x squared. So that's what this long division tells me, that this polynomial divided by this polynomial is this thing. Just like if we divided numbers, we get something divided by something is 4 and 7/8. And this dividing polynomials is an important tool for finding the zeros of polynomials. That's really how we're going to use it. So questions on how we did this. We'll do another example of long division in just a second. All right. So what we've done here with this example is we've used what we call the division algorithm. And the division algorithm guarantees us we can always do that. The division algorithm tells us is if we have two polynomials, f of x, and we're dividing by d of x, two polynomials. And if this is an improper fraction, and when we talk about numbers, if we had a fraction made of numbers, and our fraction is improper, what do we mean? The numerator is bigger than the denominator, right? 10/3 is an improper fraction. Usually we want the numerator smaller. So when we're talking about polynomials, what that means is the degree of the numerator is bigger or equal to, greater than or equal to, the degree of the denominator. So if our numerator is a 5th degree polynomial and the denominator is a 2nd degree polynomial, that's going to be an improper fraction. So if that's the case, if we have an improper fraction, we can always find some polynomials q of x and r of x, so that our fraction f of x over d of x equals q of x plus r of x over d of x. And that's what we just did in our last problem. We said that those two things, when we divided them, this divided by this was this polynomial plus the remainder divided by our original thing that we divided by. So the division algorithm guarantees us that we can always do this if this is an improper fraction. I can multiply through by d of x, multiply both sides by this, whatever that polynomial is. I could write this as f of x equals q of x times d of x plus r of x.
So what if you don't have an improper fraction?
If you don't have an improper fraction, then you don't divide. All right, and all of these things have special names. F of x is the dividend. D of x is the divisor. Q of x is the quotient. And r of x is the remainder. So the division algorithm just tells us if we have an improper fraction, we can always do long division and find these polynomials. So that's really all we're saying. We can always do long division if we have an improper fraction. But this remainder tells us something special about our polynomial and how it relates to this divisor. So let's look at another example of long division, and then we will talk about a shortcut. So let's divide 4x plus 5 into 4x to the third minus 7x squared minus 11x plus 5. So we're dividing this cubic polynomial by a linear polynomial. So the degree of the numerator is going to be 3, the degree of the denominator is 1. So it would be an improper fraction, so we can divide. So I say, what do I have to multiply 4x by to get 4x to the third? 4x squared, right? 4x squared times, or not 4x, just x squared. X squared times 4x is 4x to the third, right? So I write that there. X squared times 5 is 5x squared.
But you don't worry about the plus 5 or the next part of the number.
No, you just worry about this, whatever this first one is. Then I'm going to subtract. 4x to the third minus 4x to the third is 0. Minus 7x squared minus 5x squared is minus 12x squared, and I bring that 11x down. And then I say, what do I have to multiply 4x by to get negative 12x squared? Minus 3x. Multiply that, I get minus 12x squared. Minus 3x times positive 5 is minus 15x. Subtract. Those go away. Minus 11x plus 15x is 4x. Bring that 5 down. And what do I multiply 4x by to get 4x? Plus 1. 1 times 4x, I get 4x. 1 times 5 is 5. Subtract, and I get a remainder of 0. And we'll talk in just a little bit about what that tells us when we get a remainder of 0. So this tells us that 4x to the third minus 7x squared minus 11x plus 5 divided by 4x plus 5 equals x squared minus 3x plus 1. All right, questions then? Now let's talk about a shortcut for long division. Shortcut only works in certain places, so sometimes we have to do long division. Our shortcut is synthetic division. Not really a shortcut. We just simplify things a little bit. So synthetic division works only when we're dividing. By something that looks like x minus c, where c is some number. So, and we don't have any numbers in front of the x. We don't have an x squared. We don't have any. It has to be something in the form x minus c. That's the only time synthetic division works. C is just a number. So I just want to do an example to show the process. Synthetic division is really quick and easy. So 3x to the third minus x squared plus 2x minus 3 divided by x minus 2. Degree of the numerator is bigger than the degree of the denominator, so we can divide. So what we do for synthetic division is I write only the coefficients. So I'm going to write a 3, a negative 1, a 2, and a negative 3. I write my division thing kind of upside down. And I'm dividing by x minus 2. So I put that 2 out here, x minus 2. And then what I do is I bring this first number down. I multiply. 2 times 3 is 6. Write that there. These numbers I add. So when we're doing synthetic division, all we have to do is multiply and add. Yes? So the reason we don't put negative 2 here is so that we can add when we're doing synthetic division rather than subtracting. It's always adding. So with synthetic division, we always add. We don't have to deal with the subtraction. That's why we do the opposite sign. All right, so we add these. Negative 1 plus 6 gives me 5. I multiply these two. 2 times 5 is 10. Add these two. 12. Multiply these two. 24. Add these two. 21. This is my remainder. So this tells me that this equals, I've divided a cubic third-degree polynomial by a first-degree polynomial. I'm left with a squared polynomial, a quadratic polynomial. So I get 3 x squared plus 5x plus 12 plus my remainder over my divisor. So synthetic division quite a bit quicker, quite a bit easier than long division.
So you go like a degree down?
Yes, so we divided a third degree polynomial by a first degree polynomial, so we end up reducing the degree by 1. And our remainder is 21. So this is our polynomial. This remainder, we'll talk about what this remainder tells us in just a second.
Wait, so where do you get the 6, 10, and 24 from?
So I always bring that first number down. 2 times 3 is 6. I write that there. Add. 2 times 5 is 10. Add. 2 times 12 is 24. And then add. Yes?
How do you know that it's a remainder? The last one?
The last one's always a remainder.
Okay.
Yep, the last one's always a remainder. No, you could not do synthetic division with x squared minus c. You'd have to do long division. So synthetic division only works if you're dividing by this something that looks exactly like this. All right, let's look at another example. So when we're doing synthetic division, we always want our polynomials to go in decreasing powers. And if we're missing one, we have to put in a placeholder. So if we had 8 plus 6x plus 5x to the third, and we divide by x plus 2. All right, so what do we have to be careful with here? One, this is in the wrong order. So let's write it in the right order. Not the right order, but just descending order. 5x to the third. Plus how many x squareds do we have? 0. I have to put a 0x squared in there. That's true for synthetic division or long division. I have to put in a placeholder. Plus 0x squared plus 6x plus 8. So now I'm in descending order. And this is x. We need to divide by x minus c. So this is x minus what? Negative 2. So now I can do my synthetic division. I'm going to write my coefficients. 5, 0, 6, 8. And I'm dividing by x minus 2. So I put the minus 2 out here. Bring this one down. Multiply. Add. Multiply. Add. Multiply. And add. And this one, the last one, is my remainder. Pretty easy. Synthetic division is pretty easy. So this tells me that 5x to the third plus 6x plus 8 divided by x plus 2 equals 5x squared minus 10x plus 26 minus 44 over x plus 2. And this remainder also tells us something important about our polynomial as well. And we'll talk about that next. All right, questions on that synthetic division problem?
What is the reason for this?
We'll talk about that next. All right, so we have two special things that we're going to use division for. One is called the remainder theorem. This remainder is important. The remainder theorem tells us that if we have a polynomial, f of x is a polynomial, and we're dividing this by x minus k, the remainder is f of k. So f of x is a polynomial. We divide by x minus k. The remainder is f of k. So that gives us, if we plug in k into our function, the remainder tells us what that would calculate out to. So if we go back here to these other examples we did, this tells me that f of minus 2 equals negative 44. That's what the remainder theorem tells us. For this problem, f of positive 2 equals 21, equals the remainder. If we go all the way back to our first example, this tells me that f of 3, I didn't do synthetic division, I did a long division, but the same thing still holds, equals 4. So the remainder theorem gives us a way to evaluate the function without plugging in and calculating. So if we have to evaluate a function, we don't have a calculator, synthetic division gives us a way to do that. Find the remainder. The remainder is the function evaluated at that particular number. Here we had a remainder of 0. Now this is an x minus c. I could rearrange this to be like x minus c, but this tells us something special when I have a remainder of 0. So let's talk about what that is. That is, we call the factor theorem. If we look at the remainder theorem, what if our remainder was 0? What does that tell us that f of k equals? What is it? 0. If remainder equals 0, f of k equals 0. Well, we listed the other day a bunch of, well, 4, I guess that's a bunch, 4 things that were equivalent to f of k equals 0. The important thing that we get from the factor theorem is that if the remainder when f of x is divided by x minus k, is 0, that tells us x minus k is a factor. So if we were factoring, if we were trying to find the zeros of our polynomial, x minus k would be one of the parentheses that we had in our polynomial. So if we look back here at number 70, x minus negative 2 is one of those factors because 2 is one of the zeros. So that's what the factor theorem tells us. Is that's going to be a factor. It tells us that f of k equals 0. Or the other equivalent things that we said, if f of k is 0, x minus k is a factor, what else does that tell us? Our function equals 0 at a point. What other piece of information do we have? The x-intercept. Very good. That tells us that the point k0 is an x-intercept. That also tells us that k is a solution to f of x equals 0. f of k equals 0, that's what we said here. Also means that k is a 0 of f of x. So if we do a synthetic division, we get a 0 remainder, we get a remainder equal to 0. We found a solution to the equation f of x equals 0. We found an x-intercept. We found a 0 of the function. We found a factor of our original polynomial. So that lets us, we have one set of parentheses that our polynomial is going to factor into. So what we're going to do as we move forward is we're going to come up with a way of finding numbers that we do synthetic division with that will possibly give us zeros of our polynomial. So we can factor our polynomial, we can find all the x-intercepts. We want to completely factor our polynomial, we want to find all of our x-intercepts, we want to sketch a graph, we need to factor. So that's what the factor theorem helps us to do. We're looking for the remainder to be 0. And if we factor a cubic polynomial, we go back here, we end up with an x squared minus 3x plus 1. We could then either factor this or use a quadratic formula to find the other zeros of our function. And then we would have all the factors of our original polynomial. We'd have our 3 sets of parentheses that would give us this cubic polynomial. So that's where we're going with this, with the factor. So today we're just going to practice with synthetic division, a little bit of long division, to decide if we have a factor, and to evaluate our function using the remainder theorem. Tomorrow we'll talk about how we pick numbers that possibly can be zeros of our polynomial. All right, so our factor theorem is just this part, but all the things we wrote after mean the exact same thing. Okay, questions? I made a couple small changes to the homework that's on the board. There we go.